Hey guys, so here we are. This should be the last content video that I post other than the lectures next week. And this covers the last part of the course, which covers orthogonal complements, orthogonal projection, and minimization in the sense of least squares. Axor, of course, doesn't call it least squares, but that's what it is. So I'm going to walk you through what I'm going to talk about on probably Wednesday and Thursday. And then we'll be done with the course content. So congratulations for making it to the end here. There is, of course, further content. If anybody's interested in continuing, then let me know. And I can bridge you in to the summertime, or if you want to do independent work in linear algebra, I'm full of mathematics. And so I'm happy to talk with anybody that's interested in continuing. Okay. So what we're going to do is we're going to take the idea of the basis that we came up with last time, the orthonormal basis, and we're going to use that in an inner product space to set up the idea of projection onto a subspace. It's actually, so this idea of orthogonality is going to let us come up with the idea of perpendicular spaces. And once we have perpendicular spaces, then it's very easy to project onto one or the other of them. So this is kind of the ultimate reason why we learned about direct sums, is like for this application. So first I'm going to share the screen on my laptop like usual. And once that is broadcasting, and we'll pull up my notebook. And we will begin. So basic idea that we want to talk about, the first idea. So remember, we want to remember that we're dealing with the idea of an orthonormal basis. So we have this idea now, right? That every subspace / vector space has an orthonormal basis. And further, that any orthonormal set can be extended to be an orthonormal basis. So point one, every subspace or vector space has an orthonormal basis, and two, any orthonormal set can be extended to be an orthonormal basis. For the whole space. So we're going to begin with the idea of orthogonal complements. That's the first thing that we want here. So start with a vector space V. So we're going to start with V. And then we're going to define a subspace inside of V. So that don't even subspace, just a subset. Doesn't have to be a subspace. We start with a subset. So U is a subset of V. Once we have that, we can define the orthogonal complement. The orthogonal complement of U, sometimes people will say the orthogonal complement of U in V, which is denoted U with a little perpendicular sign up here to indicate that it's every vector that's orthogonal to U, is the set U perp, sometimes it'll get called that, U perp, or the orthogonal complement of U, which is equal to every vector V in V that has the property that the inner product of U with V is equal to 0 for all U in U. So this is pretty easy to imagine in certain contexts. So in R2, for example, if you gave me a line and called that U, and you asked for the orthogonal complement of U, it would be every vector that's perpendicular to every vector in U, which would be this line. So this is the set U perp, because every vector here, every vector in this direction is orthogonal to every vector in this direction. So you can see that what it does is it takes the vector space V and it takes it apart in terms of U and a space that's perpendicular to U. So it's in fact, it shouldn't be difficult to believe that there's going to be a direct sum structure running around in the background here. Let's take a look really quick at what this looks like in R3. So in R3, if you gave me some kind of vector in R3, to say V kind of pokes out like this, where maybe it's set up in this way, then the set of vectors orthogonal to that. If this line here, if this is U this time, is this line sort of pointing this way and coming out this way, then the orthogonal complement of U is the plane that that vector or that line is normal to. So I guess a better picture may have been like this. If you have a plane as U, then its orthogonal complement is the line that is perpendicular to that plane. And if you were given a line that is U, then its orthogonal complement is the plane that it is normal to. That's a better job of being normal here. Then this would be U perp. So the orthogonal complement is a really, really useful way of pulling a vector space apart. Once you've identified a subspace or a set that you're trying to sort of decompose a space into. Okay. So let's look at some basic properties of orthogonal complements. So this is a theorem. Axler calls this 646. Some just real easy properties to show. If U is a subset of V, U perp is a subspace. B, the set of vectors, the orthogonal complement of 0 is the entire vector space, because of course 0 inner product of anything is 0, and so 0 is orthogonal to every single vector. The orthogonal complement of a whole vector space is just the 0 vector, because the only vector that is orthogonal to every vector is 0. D, if U is a subset of V, then the intersection of U and its orthogonal complement is just the 0 vector. That shouldn't be hard to believe. And finally, if U and W are subsets, of V, and U is contained inside of W, then the set of vectors perpendicular to W is contained in the set of vectors perpendicular to U. This one's a little bit trickier to see, but the idea is it's if you have a smaller set, more things are going to be perpendicular to a smaller set, right? So if U is smaller than W, rather, so if U is contained in W, then more vectors are going to be perpendicular to U than can be perpendicular to W. And you could see that by looking at this example right here, where we had this relationship between U and U perp. When U was bigger, U perp was small. And when U was small, one-dimensional, U perp was big, two-dimensional. So there's a relationship between dimension and orthogonal complements as well. We should probably look at least part of this proof. Let me at least walk you through how the subspace argument works. So let's show that. So let's let U be a subset of V, and we'll show that U perp is a subspace. And we'll show that it's a subspace using the typical subspace condition check. So we'll show that it's closed under addition, and we'll show that it's closed. We'll show zeros in there, it's closed under addition, and it's closed under scalar multiplication. So pretty obviously U is in there, or sorry, 0 is in there, because 0 U is equal to 0 for all U and U, because the 0 vector is perpendicular to everything, which means that 0 is in the perp of U. Let's assume that we have V plus, we're going to show this closed under multiplication now. So let's suppose, sorry, not multiplication, addition. Suppose that we have V and W in U perp. And we're going to show that V plus W is in U perp. So what does it mean to be in U perp? It means that you are orthogonal to every vector in U. So we'll start with this expression. V plus W inner product with U for some U in U. Really, I guess if we're going to be more precise here, we should be arbitrary and say, let U be any element in U perp, sorry, in U. So an arbitrary element in U. And now we're going to pick, we're going to look at this inner product, V plus W with U. And by linearity, we're going to get VU plus WU. But this equals 0 plus 0 because V and W are in the perp of U. And that implies that V plus W comma U is equal to 0 for all U in U. And that implies that V plus W is in U perp. So we've shown zeros in the set. We've shown that it's closed under addition. And now we'll do the same thing and show that it's closed under scalar multiplication as well. So for step 3, let U be an arbitrary vector in U. Let V be in the perp of U. Let lambda be in the field. Then lambda VU is equal to lambda VU, which is equal to lambda times the 0 vector because V is in U perp. And that implies that lambda VU is in the perp of U for all V. In U perp. And so we're closed under scalar multiplication. This was closed under addition. And this was contains 0. And that lets us conclude that U perp is a subspace. Now you might wonder, if U is a subset, is there any way to get the subspace that contains U? And the answer is yes. There's a couple of different ways to do that, but the easiest way to do it is to take the perp of the perp, and I will positive that that is a homework exercise. So I'll leave that to you to solve. And the rest of the properties follow sort of similarly and are much easier. This big structural result that we want about orthogonal decompositions is that if we start with a subspace, then the space and its orthogonal complement actually immediately form a direct sum decomposition of vector space V. So this is a really important theorem. So if we start not with a subset now, but an actual subspace, if we let U be a finite dimensional subspace of V, and I haven't said it yet, but I should. V here is assumed to be an inner product space, so that the idea of taking an orthogonal complement even makes sense at all. So if U is a finite dimensional subspace of V, then V is equal to U direct sum U perp. This is a pretty easy argument to show. I'm going to remind you guys how one of these direct sum arguments goes. The way that we do this is we are going to show that V is contained in the sum of those two spaces, and then we'll prove that then we'll just assert actually that since a space and its complement intersect trivially just at the 0 vector, then it's actually a direct sum. So let's show that V is equal to u plus u perp, which means every vector in V can be written as a piece in one and a piece in the other. So let V be an element of V. And let's let E1 up to EM be an orthonormal basis for U. And then we're going to decompose V into two parts. So we're going to take a V, and first we're going to compute its coordinates expanded into U. So we're going to let V be equal to V1, E1, E1 up to V, N, En, En. And then we're going to add that to V minus that vector, which is just a cheesy algebra trick, right? Vn, En, En. That's an algebra trick. Of course, this is equal to V because here's a V. This is a positive bunch of vectors, and here's the negative of those same vectors, and everything cancels, and all you're left with the other side is the V. So we've just uncanceled something really fancy. But notice, this is the same trick when we were talking about orthogonal decomposition of a vector. If we call this vector U, and we call all of this stuff W, by the theorem where we talked about orthogonal decomposition, it must be the case, actually, that W is orthogonal to all of the basis vectors EI. The W is in, that's actually pretty easy to see. I guess maybe we should actually compute it real fast, because the inner product of W with EJ is equal to VEJ minus VEJ. Where did that come from? That came from the definition of W here. If I take this this vector and I sub W out for that, and then I use linearity of the inner product, you end up with this statement, which is just 0. So you should, if you don't see what's happening here with like W being put into this inner product, you should actually write the substitution down and work your way through it. This is something that we saw before in an earlier argument. Since W is perpendicular to every EI, that means W is perpendicular to everything in the span of the I. So W is orthogonal to the span of E1 to En. And that means that W is an element of the orthogonal complement of U. And what that means is this expansion right here actually wrote V as something in U, because it was expanded in terms of a basis for U, and something in the orthogonal complement because the W vector that was left over was perpendicular to U. So what we've shown is V is equal to U plus W, U is in capital U, W is in U perp, and so big V is equal to U plus U perp. And then by the argument we wrote earlier, but the theorem before says that a space and its orthogonal complement intersect trivially. That's going to give you the direct sum. Since U intersect U perp is the 0 vector, V is actually a direct sum of U and the orthogonal complement of U. And that's a really useful fact. Okay, let's see what else we can say here before my poor pencil dies. There's a dimension theorem that you should. It's not hard to believe this is true. This one is this is just immediate from the rank nullity theorem, or sorry, the fundamental theorem of linear maps. The dimension of a vector space is equal to the dimension of U plus the dimension of the orthogonal complement of U, because it's a direct sum. And so that means that you can always calculate the dimension of an orthogonal complement just by taking the dimension of V and subtracting the dimension of U. That's true. And then, and this is an argument I want you guys to read because this is a cool one. This is a cool idea here. If I take a space and I take its orthogonal complement and I take the orthogonal complement of that, then I get the original space back again if U is a finite dimensional subspace. And that's a really, really, really nice geometric property here. So to you guys, this one, I assign the proof. That's not so bad. It's a double inclusion argument, right? So the setup here is that you're going to show that U is contained in the perp of U, and then you're going to show that the perp of U perp is contained in U. So two different arguments, but you get a double inclusion, which is going to force the sets to be the same. Okay. So let me check how long this has been recording so I can decide if I'm going to record the second half of this video in the same thing. How do I check that? Can I check that? I don't know. I don't actually know how to check that. Okay, so what I'm going to do is I'm going to leave this off, and this part of this video I'm going to leave off as the first part of 6C. And this is basically, so the upshot of what we did here, I guess, so the upshot is that what orthogonal complements let us do they let us take vector spaces apart into direct sums in a really easy way. And that's kind of the sort of the big idea of what you would want orthogonal complements, is that if I give you a subspace and it happens to be your inner product space, automatically you get an instant direct sum structure. And better than direct sum, because it's a direct sum where the actual spaces actually turn out to be orthogonal to each other as well. Prior, we had the idea of direct sum without orthogonality. This is sort of a way, way better version of direct sum, because now not only does the space decompose, but it decomposes into pieces that don't see each other at all. Okay, so I'm going to leave this off. And in the next video, we're going to talk about projection onto subspaces and solution of like minimization problems, or like solution of problems by projection, where I guess this solving an impossible problem that we talked about earlier. All right, see you guys in a minute.